Welcome. Today, we're going to explore a powerful machine learning algorithm called gradient boosting. Let's start with an analogy. Imagine a team of students trying to solve a complex problem. The first student makes an attempt. They get some things right and some things wrong. The second student doesn't start from scratch. Instead, they focus only on the mistakes the first student made. A third student then looks at the remaining mistakes and tries to correct those. Each new student learns from the combined errors of the team before them. By combining all their efforts, this team of weak students can produce a highly accurate final answer. This is the core idea of gradient boosting. Let's apply this to a real-world problem, predicting house prices based on their size. Here is our simple dataset. Our goal is to build a model, f of x, that takes a house size and predicts its price. Gradient boosting starts with a very simple initial prediction. For regression problems using mean-squared error, the best starting point is simply the average of all the actual values. Let's calculate the average price from our data. So our initial model, which we'll call f0 of x, predicts a price of $365,000 for every single house, regardless of its size. This is our first, very weak model. It's not very good, but it's a start. Now, we need to figure out how wrong our initial model is. These errors are called residuals. In gradient boosting, they are specifically called pseudo-residuals. Why pseudo? Because they are the negative gradient of our loss function. Let's see what that means. For regression, we often use the mean-squared error, or MSE, as our loss function. The gradient is the derivative of the loss with respect to our model's prediction, f of x. It tells us how the loss changes as our prediction changes. The pseudo-residual, r, is defined as the negative of this gradient. Plugging in our gradient, we get negative of negative, which is just the actual value minus the predicted value. So for MSE, the pseudo-residual is simply the true value minus our current prediction. It's the mistake our model is making. Let's calculate the residuals for each house using our initial model f0, where the prediction was 365 for everyone. These residuals represent the errors our first model made. Notice that for smaller houses, the errors are negative, and for larger houses, they're positive. There's a pattern here. Now we fit a new, simple model to predict these residuals. This model's job is to find the pattern in our errors. We'll use a very simple decision tree called a stump, which only has one split. Our new training data isn't price versus size, it's residual versus size. We're asking the tree to predict the error for a given house size. Let's say our simple tree finds the best split at a size of 1,700 square feet. For houses smaller than or equal to 1,700 square feet, we calculate the average of their residuals. For houses larger than 1,700, we do the same. This tree, let's call it h1 of x, has learned the main pattern in our errors. It knows that our initial model was under-predicting for large houses and over-predicting for small ones. Now we update our main model. We don't just add the full correction from the new tree. Instead, we take a small, cautious step. This is controlled by a parameter called the learning rate, often denoted by alpha or eta. A smaller learning rate, like 0.1, makes the model learn more slowly, but often results in better overall performance. Let's use a learning rate of 0.1 for our example. The update rule is the new model equals the old model plus the learning rate times the prediction from our new tree. So our new model, F1, is our initial model, F0, plus 0.1 times the correction from our first tree, H1. Let's calculate the new predictions, F1, for two of our houses. First, a small house of 1,000 square feet. The tree H1 predicts a correction of -105 for this house. So, the new prediction F1 is 365 plus 0.1 times -105. The prediction moved from 365 down to 354.5, which is closer to the actual price of 200. It's an improvement. Now for a large house, 2,200 square feet. The tree H1 predicts a correction of +105 for this one. The new prediction F1 is 365 plus 0.1 times 105. This prediction moved up from 365 to 375.5, which is closer to the true price of 480. Again, an improvement. We have now completed one full boosting round. The algorithm is iterative, so we repeat the process. We start again from step 2, calculating the new residuals. But this time, we calculate the residuals based on our improved model F1. Here's a table showing the original predictions F0, the new predictions F1, and the new, smaller residuals. Notice the new residuals are smaller in magnitude than the first set. Our model is getting better. The next step would be to train a new tree, H2, on these new residuals. We would then update our model again. F2 of x would be F1 of x plus our learning rate times the predictions of the new tree, H2. This process repeats for many iterations, each time adding a new weak learner that corrects the remaining errors of the ensemble. Let's summarize. Gradient boosting builds a strong model by sequentially adding weak models. In each round, we calculate the errors, or pseudo-residuals, which are the negative gradient of the loss function. We then fit a new weak learner, like a small decision tree, to predict these errors. Finally, we add this new model to our ensemble, scaled by a small learning rate, to update our overall prediction. By taking many small, incremental steps, each one targeting the remaining errors, gradient boosting can create highly accurate and robust predictive models, widely used in everything from search ranking to medical diagnosis. Thank you for learning with us.